energy and the cost. Lower energy is because the ILC has been staged to lower energy, and for CPC it's the same. And we try to reduce the cost by reducing the radius, the number of layers, the magnetic field. Those are the main components on which we can play easily, let's say. Now, doing so, and redefining everything is not an easy task. There are a few numbers which are fixed. One of them is the radius of these elements. For mechanical reasons, this is 40 millimeter of radius. And if you want to fix the radius, here you have first to look at the end caps to put an integer number of wafers into or on cassettes. And that will fix the outer radius of this guy, and then you have to count down the number of layers and everything you put there to get the internal radius. For the length, this is just the opposite. You have to define the length of this element to know where to put the end caps and the rest. Okay, plus there are some utility parameters like space to put the cables and an overlap here so that you don't get any loose element in the coverage. After that, you have to ensure that everything works properly, and this requires some mechanical simulation, and depending on the situation where you are, that can be either just static mechanical simulations or dynamic, like in Japan with the earthquakes, and that will define for the precision you need to put on the stiffness of your elements. You see there with an increased zoom, the deformation, but also to fix the margin you need between those elements during construction and for the running. And you see here that this is scheduled to be quite small, to have this small space between the two modules in the barrel. In addition to that, one has to put there also the simulation of the cooling. All the cooling should come at the end of the module, of the slabs, only on one side, so you will see one part where it's heated. You have all the heats which accumulate, and it should be evacuated here. And that's really one of the critical points which is really different between the ILC and CPC. This is this power pulsing capacity we have ILC, and that in CPC we don't have. So that was an old simulation with an active cooling of the chips, how you can draw the heat from the chips which are working in continuous mode at the CPC. And that's a new one that has been done recently at SGTU, just by putting an array of chips heating and see how much you can cool by different thicknesses of copper. And the question is how much copper you can offer in the detector before you switch to active cooling, which is something, another development. So the first very preliminary results hint that 5 millimeters is not enough, so that's probably an overkill for passive cooling. It has to be confirmed still. For the cooling, you see that this is quite involved already, to where to put the pipes, everything, etc. And this also affects the way the DIQ is made, because we want to have a pipe here for the cooling, and around that all the cards for the acquisition, on which on this side you have only 5 centimeters between the ECAL and the HCAL. So that's also some work which has been restarted very recently. This is how to make a compact DIQ in such contained space. Also putting the power supplies and high voltage, etc. So that's we should get something up to date soon. The simulation was also completely rewritten recently. It's much more flexible in this framework, the D4HEP, modular code. You can do more configuration, and there is one nice feature that has been added, which is to have dual simulation, in which you simulate at the same time the scintillator and the silicon versions of the ECAL. The other version, the other material serves as the mock-up for the PCB when you are looking at one of them. There was some discussion on that, and this should be started really soon to have massive production on there. And we added also some things we forgot, like plugs at the end to stick the material in the alveolar. Okay, so Henri Vidot is doing lot of work these days to put all those information in one document on which everything is referenced with consolidated definitions, all the numbers restarted, including the cost. So that should come also this year. And there are still some elements, as I said, which are not fully there, like the IQ, the grounding scheme, etc. Okay, now I start with the CALICE application. How do we get from this design that I've just shown you to something which is working? We build some prototypes, and the first thing, the very basic element of the prototypes are those so-called ASU boards, which is just a PCB with 4 silicon wafers glued on them. And that's what we are testing in beam test for prototyping and checking that everything works. If you just make the counting of how many elements you need from that, you need of the order of 10,000 slabs, and we have roughly a third of it. I'm talking here about the long slabs. If you count the ASU, we have a bit more of them, but we are still way far from complete production. Nevertheless, we have 20 of them, but we are able to test 7 of them in the lab. So this is just the history of everything. You see that the work has started really in 2007 on this. And this shows a nice exponential progression, so you can extrapolate how long it will take to get the full detector. Okay, so on those short slabs, we have a full assembly chain that has been set up in the Paris region. And this allowed to make 10, in production of 10 in 2016. You see that we receive elements in the different labs and make them, test them. That's with a full data quality procedure, so we try to record everything. It's not perfect yet, but okay. And that's what we got working in 2017. So 7 layers that we were able to bring to beam test at DAISY. And those were actually the first very successful beam tests where everything worked as expected. And the results are really nice. So you see here a scan of, so this is a figure of one slab with 16 chips. You see that the pedestal position is dominated by the chip themselves. And we made a scan here with electrons in punch-through mode, so they were used as MIP. And the first thing we wanted to check was the signal-to-noise ratio, and we got actually something which was almost unexpected, of the order of 20 for this signal-to-noise ratio, defined as the MIP position, most probable value, divided by the width of the noise pedestal. And this allows actually to set up the auto-trigger level at a third of a MIP, so it means we have 100% efficiency on every MIP entering the detector in auto-trigger mode, and that's really an achievement of almost 10 years of work. We see also that the pedestal is relatively stable, of the order of 10% variation over time and in function of the energy which arrives in the detector. So 10% variation of MIP, sorry, I forgot to put this, so this is reasonable. So if you want more details, I push you to the presentation that was made at CHEF 2017 by Adrien Irles. We tested also the slab in the magnetic field, and that behaves as expected. It's not fully visible here, but okay. We haven't seen anything going wrong by running this in one Tesla magnetic field. So there are still some elements that we want to check. Just from a physical point of view, compared to the physics prototype we have tested before, we have 4 times the surface density in chip. We have less longitudinal density. We are going to less layers for cost issues. And we'll try also thicker wafers. Okay, and going to higher density also has some expected effects on the noise, etc. I won't go through everything there, except to mention that one thing we would like really to test soon are these timing issues. And the next version of the Skyrock 2A, we should be able to switch on the TDC, which was existing in the previous version, but that we could not use, with raw timing performances. But okay, that's just first to test. So that should be test it further. From those test beams, we identified many points that could be improved. So of the order of 15 of them were addressed in a new version of the board. So one example you see here, all those white squares were the cells masked for the triggering. So you see that there are some power lines here which are inducing some noise. And if you have good eyes, you can see also that there are some squares which are always at the same spot. This is one noisy cell in every of the chip. So we improved on all of this and launched for production an updated version of the board, which is the version 13. And that we want to test this year in a beam test. We had, unfortunately, some delay on the production due to well, that's the industrial default. So we hope we can still get them working for September at least. And there is also something we would like to try for the first time, which is this chip-on-board version, on which the chip are not packaged as here, but are embedded in the board. This allows to make a thinner design. And this version of the board has been, a new version of this board has been produced this year and is being tested and commissioned at LITE. So this is common work between Korea, CERN, and Orsay. Good. So yeah, that's just to summarize all what I said. So we'll try this new version of boards. We'll try also different thicknesses of wafers. We want to go to larger wafers. If you go to a smaller number of layers, we want to recover part of the resolution by increasing the wafer thickness. Okay, the last point that was, so those short slabs allowed us to say that we are there technically, we have all the performances which are required to build the detector, at least the element of the detector. Now we have to assess that we're able to stitch them together to slide them in the detector. And stitch them together is to put up to 12 of them, one after the other, and be able to read them and check everything. So that's what we have started between LL and LLR, and we have split the work in two. One is to make the mechanical setup on which you try to get all the mechanical precision needed, and in parallel do something where you release all those mechanical constraints, but concentrate on all the electrical effects you might expect. So those are two images of the assembly bench we have here in Orsay, and we will switch from those flat captans that we used and we realized were not exportable for industrial production to some connectors here fitting our needs. The other part is this long slab on which we glue only a very small baby wafer because this is much cheaper. And okay, we want to fill everything. Now the image doesn't show, but we have 5 of them, and we want to go up to 12. Bring that on this stage to test beam. And that's testing with Cosmics, strontium source. Unfortunately, with this source, you can highlight only one cell at a time. And what we found nice that with cesium 137, you can highlight all the cells and still get something on which you can test the calibration of the chips up to of the order of 6 MIPS. So that was really a nice discovery made a bit by chance. Okay, so that's it for the scintillator, for the silicon. I have a few slides on the scintillators as well. So the scintillator actually used the same structure here, only in the slabs where you have those double layers. One would use those 5 millimeters strip of scintillators, read at one end by a silicon photomultiplier. And you would have one layer oriented in one direction and the other one in the orthogonal direction, so that you can reconstruct the position with higher precision, which is basically the size of the width of this strip. The boards are based on the ECAL board that maybe Jamel will describe later. And there were some prototypes made, which 144 of such strips and put in test beam. So those boards controls everything, including LED for calibration. And one of the key elements is this scintillator photomultipliers, which needs to allow to check the full range of the dynamic range that you expect in one of the strips, which is of the order of 1,500 MIPS at high energy. So it's probably a bit less than that, but you can see that with a 10,000 pixel chip, you can achieve that. Of course, with some corrections. This is the linearity, but you still see you have some sensitivity here, even at very high light fluxes. So the key element there, the other key element there is the size of the pixel on those silicon chips and the noise, which would you get spontaneously, the dark noise. This dark noise was really high, but during the last few years, it has decreased dramatically. So that was really a very nice thing. Still, they are fighting with that. You see here some readout of those are MIPS on a test bench. So you expect of the order of 10 photoelectrons per MIP with the basic scintillator they first used, 14 with an improved one. Nevertheless, this is too low actually to get really a nice signal. This was the best image they could get of a MIP in the full setup. Putting the threshold here, you see there is still a noise which goes through, and after that the MIP is cut. So it has to be improved, and actually it can be improved by using even larger pixel sizes. And also by using wedge geometry here. If you put this kind of scintillators, you can pack everything without any hole in the efficiency, because you collect more light near the silicon PM, which is there, than in the rest of the strip. And doing that, you can improve that. It's still not yet perfect, but it's on the right way. This is with electromagnetic showers. Just for this design, this is for uniformity, but you also gain by solder directly the silicon PM on the board. So there are still some brainstorming on how to improve things, and there are some ideas like cleaning up the both sides. This is some work from Kyushu University, and checking the uniformity it can get. And the Chinese group also started to work on this, making some simulation of the response here, depending on the position where you put the silicon photomultiplier. And putting it in the middle was thought to be the best response. Now this is only simulation, it has to be tested with prototypes. Okay. Good, so this summarizes a bit everything what I said. We are fairly advanced now on the silicon side. I think we have really last year reached a major step, which is to check that all the technological steps on the basic unit are fulfilled. We are optimizing the rest of the things. Last version of FEV or the thinner version, checking for larger wafers. And there are still this last piece that we are working on. And okay, we are fairly confident that we'll go through. What remains to be done is timing issues and cooling. And for this, I will forward to David. Dave for the work which is made on ECAL, which is much closer for the CPC than what we do. And there for CPC, there is still the question of having the final chip. As I said, that should be closer to that, and running with a central trigger, which is quite different from what we use for the ILC. For scintillator ECAL, they are not so advanced. This is really my personal opinion. There were some progress on SIPM, but still the performances on integrated device is really something which is not easy. This we have seen for the silicon, and there are still quite some work also from the scintillator side. So building prototypes and addressing all the technical issues, it takes time. Okay, so I'm done.
Thanks so much, Vincent. Any question, comment? Massimo?
I have a list of questions, right? But they are small questions. So let me start by the first one, and then I jump to the last one, and we see whether we have time in between. So I probably missed the point, but what is actually the power dissipation in milliwatt per centimeter square that you can expect in your slab?
In millimeter square.
Or whatever unit, just to write down a number for me.
I will address to Stefan. I remember something of, yeah. And this is with this
okay,
5 by
yes.
5 square millimeters, but after that,
Okay, and then in your cooling system, which is the temperature gradient that you have along the slab?
So for the cooling, this is passive cooling for the ILD side. So we have 400 microns of copper.
Yes.
And this takes the heat to the end of the slab, and there is a cooling a caloduc, which is just taking the heat out with some water system.
Yeah, but what is the temperature variation that you have along the slab?
Of the order of 6 degrees.
6 degrees?
Yes.
Okay. Then the other comment, okay, I have others, two very short. I mean, what is the reason for requiring the time stamping?
Okay, so there are several reasons. One would be to ease to the particle flow reconstruction. You can dismiss the delayed neutrons as well.
For the delayed neutrons.
And the photons which are bouncing back from one shower to the
so they are off
part.
with respect to the BCO,
And the other part is particle identification.
Okay, no, but this is fair enough for me. Okay, yeah. Then the final question, your comment about the silicon photomultiplier response. I mean, there, obviously, you're testing and qualifying with a strontium, and so strontium source or whatever radioactive source. Mm-hmm. So you're actually working in self-trigger mode. But as long as you work in sync mode, then the problem of the, say, the low detection and the DCR is gone.
Yes, yes. No,
am I right?
Not completely gone.
Not,
but
of course, not completely, but very much reduced. Yeah. So again, the signal will be a lot cleaner because it's occasional and random, and if you scale it up, the probability that you have a pile up there count overlay to your signal is very small.
Yeah.
Okay.
I agree. It's easier with the central trigger.
Okay, thanks.
But in ILC mode, it's not the case.
No.
In ILC mode, it's not the case. We are triggerless. So
but you open the gate in sync mode. You're triggerless, but you...
We are taking data during the...
Yes, but it's synced to the BCO. Huh?
Let's stay to circular collider. Okay. Any other...
So I have a comment maybe on your second last slide where you show the...
You have the number?
Yeah, this one. This slide. And actually, I'm not sure if you were in this morning's session of the calorimeter. No. There was a report.
Yeah, I just arrived minutes ago.
I see about the CEP, the ECAL status.
Yes.
And in that report, actually, we showed the actual experimental result on this uniformity test of this kind of a coupling, from the bottom surface, and it did give us a very good uniformity.
Uniformity, yes. With a small dent here or
in the middle.
Yes. I've seen that. I haven't mentioned it. It's actually very similar to what is done in the AHCAL.
Yes, exactly. Yes. And also, I would like to mention that another advantage of this coupling scheme is that it would allow us to use a large size SIPM, which could give us, a large dynamic range.
Yeah, but sorry, it It's not exactly similar to ECAL here because the thickness is less. So putting the silicon PM, as it was mentioned this morning, is not a trivial. Especially you will have to add the thickness, this additional thickness.
No, we'll make a hole, small hole.
Yeah, but it's difficult to be done with this very thin scintillator.
We have done it. But
Okay.
not a large scale, yes. But, yeah.
Any other?
Maybe another, if we still have time. I remember you showed a slide showing, the SIPM dynamic performance with this one.
Yes.
So I wonder what kind of SIPM is this on the left side?
I don't have the reference. I should check it up. Yeah.
Because I see the the name put on the slide, Liang.
This one there. You mean?
Yeah, is that basically picture corresponds to the plot in the middle, showing the the energy spectrum.
I should check this. Yeah.
Yeah, I just wonder if there's any connection between between this SIPM and the plot.
Okay. I have a very short question. You mentioned the time resolution about 1 nanosecond, something like that. But this is what you want, or is still far? How much do you want?
This is what we have.
Yes, and what do you want?
All the studies made by the CMS at ECAL actually really started a lot of thinking about this timing, what could bring the timing. So ideally, you would like to go to of the order of 50 picoseconds or less.
50.
To do this time of flight.
Well, okay.
Yeah, that's for showers. For a shower, yes, you should average that over a full number of cells. Yeah. No, MIPS is. Yeah.
Okay. Thanks so much, Vincent. Let's go to the next. Thanks again.